In this video, let's check the accuracy of the sensitivity kernel, or Frichet kernel, the so-called Frichet kernel. Um, so uh, again, I'm still following the 2005 paper by Li Zhao. He has this half-space kernel here. So source is here, receiver is here, um, and then sort of this is a cross section. So let me blow up the figure. So this is the cross section perpendicular to the source receiver plane. So free surface is here, and then source here, receiver here, right? Right. So we are looking perpendicular to the source receiver plane, right? That's a plane that's passing through both the source and receiver points, and also perpendicular to the free surface, right? And then there's another cross section that's seeing a plane that's going through this dashed line. That's a cross section that goes through the dashed line. Right, so this plane is actually perpendicular to the source receiver plane. So if the kernel is accurate enough, we're supposed to see the so-called banana donut effect. So this sensitivity kernel is for the cross correlation for the broadband cross correlation travel time delay for the direct P, right? And if you are making this kind of a cross correlation travel time measurements on the broadband signal, we're supposed to see zero sensitivity on the ray path that's crossing the source that goes from source to receiver. So if you take if you look at this kind of thing, this kind of a cross section, you're supposed to see white. So white means zero sensitivity, just like the background. In the straight line that's connecting source and receiver, right? And then if you look into the plane that's perpendicular to the source receiver plane, you are supposed to see this kind of donut hole that's kind of in the middle. Water sensitivity, right? The existence of this donut hole can be used to validate the accuracy of the kernel code. So if your kernel code is accurate enough, you are supposed to see the sensitivity, so see the donut hole, if you are using the broadband cross correlation travel time as your measurements. So that's what we are going to 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 to, to compute in this particular video. Right? So let me and so in order to compute the sensitivity kernels, we basically require three basic inputs. The strain fields from the source side, that's the source wave field, right? The strain fields basically, the strain fields from the source side, and then the strain fields from the receiver side, and then something that's called a seismogram perturbation kernel, or later on I was calling it wave field perturbation kernel. The concept was introduced in my 2007 paper, I think. Where's my Dropbox? My papers. Where's my 2007 paper? Right, that's so in this particular paper I was calling it the seismogram perturbation kernel, and then in my book I was changing the name to wave field perturbation kernel. It's basically this kind of thing. For broadband cross correlation travel time, it's this kind of thing, right? So if U is displacement, if we're making measurements on displacements, not velocity. If we're making measurements on velocity, then we have to change this expression. Right? So if we're making measurements on the velocity displacement seismogram, we're doing a broadband cross correlation travel time measurement on a displacement seismogram. Then the seismogram perturbation kernel is supposed to be the derivative, time derivative of the displacement seismogram within a time window, right? Tn prime, that's like a, so h is a Heaviside function, so that gives you a boxcar to window out the waveform that you want to use for cross collision. Then that's the velocity. That's a velocity seismogram, right? Suppose if you assume u is displacement, then time derivative is like the velocity, and then you have a minus sign, and then you have to sort of normalize the whole thing with this constant. Right, this constant, this is just a number. It doesn't depend upon time, but this actually depends upon time. Right, it has time dependence. And then this is just a velocity squared, and then integrated over the time interval. So this is more like the energy, right? So the velocity seismogram within this particular time window has to be normalized by this particular constant, which is the energy. That's what we call the seismogram perturbation kernel. The seismogram perturbation kernel is basically the Fréchet kernel, or the functional derivative of the misfit measurement, which is our broadband cross correlation travel time, with respect to the displacement waveform, the displacement seismogram. Right. Displacement seismogram is a function of time, so you are taking a derivative with respect to a function of time, with respect to a function. So that's called a functional derivative. It's another kind of a Fréchet derivative. Right. But if you are making measurements on velocity seismogram, broadband cross collision velocity seismogram, the expression has to be changed. Right. It's not a difficult derivation, but it still has to be changed. Right. In my book, I talked about how to use the correct formula, how to change this formula to the correct thing. And basically, that's the seismogram perturbation kernel is just a time series, so that's relatively easy to create. The strain fields from the source side and the strain fields from the receiver side can be created by using SW4. Right, those are two very large volumes, right? Strain volumes, four-dimensional strain volumes. So they are functions of both space and time. So there are functions of both time steps and also the mesh, the spatial mesh. Right. So in previous few videos, I kind of discussed how to create those strain fields. Right. So this is in the source, in the FWF, that's forward wave fields. That's all the strain fields. So this is the source ID. Right. And then you have to create this kind of input file. That's the input file for the source. I was using a Gaussian as the source time function, and then it's an explosive source, just following the Li Zhao's 2005 paper, explosive source. So you have like three diagonal components of the moment tensor, and then all the off-diagonal elements are just the zeros, and then that's a very simple input file for SW4. Right, the velocity model is uniform half space. Right. Grid spacing is like 200 meters. I have this many grid points, that kind of thing. And then once I have created this input file, all I have to do is to execute this particular script by doing sbatch run SW4 sh to submit the job. So this is the job script for my cluster, so it's for the cluster of my university. And then inside of this script, I was just basically calling SW4 with this file as the command line arguments to SW4, and then it's gonna create all those WF files. Those WF files are binary, so I cannot see the content, but the 6 digits are just the partitions, the process IDs. So for this particular run, I was using 10 nodes, 16 processes per node, so it's like 160 processes. So in the x direction, I have used I'm using 16 processes, and then in the y direction I'm using 10 processes. So that's why it's like 15 to 9. So 15 because the process ID starts from 0. So from 0 to 0, 15, that's 16 processes. Right? 16 times 10, that's exactly 160 processes. So in a previous video, I was saying that SW4 doesn't allow partitioning the mesh in the vertical direction. So it only allows partitioning the mesh in the lateral XY direction. So that's why we have just the two process IDs, right? One for X, one for Y. And then another input file that SW4 is gonna the modified SW the SW4 modified by myself is gonna read another input file. It's gonna read this particular input file, right? It's a very simple input file. So this first line is a flag for determining to what kind of stage SW4 is gonna run, right? For 0 and 1, it's gonna write out some information data, some kind of metadata about the distribution of the mesh, and then the reference velocity model, that kind of thing, that will be used for computing sensitivity kernels later on, right? But if the first line is anything larger than 1, for example 2, an integer larger than 1, then that's going to do the full wave propagation simulation to compute the strand fields and store them. And then this is the time sampling, time decimation rate. So the strand fields don't have to be saved on every time step. So if I decide to skip some time steps, this is going to be the skip rate in time, right? The second number is added, right? So the second number doesn't exist in my previous video talking about this particular profile. This is IT shift, the number of time steps I have to shift the strand fields from the receiver side. The receiver side. So I'll come back to that later. But then this is a flag whether it's attenuating media or not. So if I want to compute the invertible Q, for example, this has to be 1. Simulations have so SW4 allows viscoelasticity. So this is a attenuation flag, and then that's the directory for storing the wave view, the information data, the metadata about the mesh and the metadata about the velocity reference velocity model, and then I deleted the one line that's a directory for storing the wave fields, because that's unneeded. That's not really needed. And then this is a flag for what kind of kernels are going to be needed. So for now, if the flag equals to 0, then I'm computing kernels with respect to bulk and shear moduli and density. So I haven't actually wrote the code for that yet. I haven't wrote the code for SW4 for this particular flag yet. Right? For AWP, I have the codes. All I have to do is to actually copy them over, make some changes, but I haven't done that yet. And then if this flag is 1, then I'm supposed to compute the lambda parameters, lambda and mu, basically. This part of the code is implemented, but the model also needs if I'm changing density, so I'll need density kernels. But for now, density kernels are not copied over yet. And then if that flag equals to 2, then it's VP and VS kernels with respect to VP and VS. Again, density kernels haven't been copied over yet. And then if it's 3 or 4, then it's anisotropic media. But SW4 doesn't actually account for it accounts for anisotropy to some extent, right? But it's not like a fully supporting anisotropy yet. At least for the mesh refinement, for mesh refinement stuff, it's not anisotropy isn't actually accounted for yet. So for anisotropic kernels, I haven't actually copied over the codes yet. So for now, there's only the one that's used most often by me is either lambda parameters or VP or VS, right? So Those kernels are actually VP and VS kernels. So that's VP kernel. Um, so if I'm using 2, which means that I'm computing VP and VS and then density kernels, uh, and then I have like 3 kernels to compute, right? But here I'm just computing like the VP kernel, the VS kernel, and then for density kernel I'm skipping it. So I have so if it's 2, I have 3 kernels, right? So I have 3 numbers here. But but if I just want to compute one of those kernels and skip some of those kernels, for those skipped kernels I have to put zeros, and then for those kernels I want to compute I have to put ones, and then the last row is actually the spatial decimation rate for the spatial mesh, right? So SW4 allows mesh refinement, so it's got like a composite mesh with different levels of grid spacing, different grid spacing. So for every composite mesh, for every component mesh, there's going to be a decimation rate. But for this half space experiment, I have just a one component mesh. Expands the entire half space. So I have just a one row, right? But if I have multiple component meshes, then I have multiple rows underneath it, right? And then on each of the row, it's gonna have like 3 numbers. That's the decimation rate on each of the direction. That's x, y, and z directions. Right, so 2, 2, 2, which means I want to decimate by a factor of 2 in each of the direction. So the simulation grid is 200 meter. After this decimation, it's going to be 400 meter, right? So the grid spacing in the decimated grid for storing the kernels, for computing the kernels are going to be like 400 meter. It doesn't have to be exactly the same as the simulation grid. So this is one of the places where we can save storage, disk storage. Right? So all I have to do is to actually make sure that these 2 files, inv.in and this input file that's also read by SW4, these 2 files exists, and then I can run this simulation. That's the forward wave field, right? And then the second thing is the receiver green tensor, right? So the receiver green tensor also have the same thing. The input file, but last time I was saying that the input file so last time I spent lots of time to talk about this input file. I was using a direct source, right? But with a time shift, I was saying that this time shift is actually exactly 3 time steps. It's exactly 3 time steps. So that's why in inv.in this number is 3 actually, right? So the RGT has to be shifted forward, shifted to earlier times by 3 time steps, right? Shifted earlier means what? Shifted earlier means when I access the array, when I access the RGT array, the time index, the index I'm using to access the RGT has to be added by 3. So if I want to access the 0th time point, I should access actually 0 plus 3. That's the 3rd time step, because the delta function, the Dirac function, is delayed by 3 time steps, right? And then all I have to do is the inv.in file is identical to the other one I was showing you, because here it's actually a soft link. So right, they are both soft links. They are links pointing to the. They are actually links pointing to the text file that's inside of the jobs directory. So and then I just run this run SW4 in this directory, and then create all the WF files. And then the next thing I need to actually create is the so-called wave field perturbation kernel, or subgram perturbation kernel. That's done using a script. it's using this particular MATLAB script that's called wpkgen.m. I was basically just reading the sidemogram that's computed from the forward simulation from the source, and then convolve with the source time function that's used for computing the Green's tensor from the receiver. And then the formula that's used here is actually it's not because I'm making measurements on the side on the velocity sidemogram, right? It's not displacement sidemogram, so the sidemogram perturbation kernel is going to be slightly different from the formula that I was showing you. From this particular formula, right? It has to be modified, I would say. And then the expression here is basically that modified formula. And then that's the time window basically. It's a tapered time window, so it's got like 4 different parameters. And then I write the WPK out. But for some reason, this WPK has to be sort of changed a little bit. So this script is written based upon just exactly this mathematical formula, but what I have found is that for some reason the sidemogram that's written out has 2 more time steps than the strand fields that I'm sort of storing by myself. The sidemogram that's written out by SW4 is read by using this particular function provided by SW4, right? So what I have to do is to actually just edit this particular. For now, I'm just doing that manually, but later on I can write a script to implement that. The problem is that so the kernels are stored inside of this directory. So that's the source ID, that's the receiver ID, and then inside of it, that's all the kernels, and then that's the WPK. So from the calculation itself, all the non-zero parts of the WPK are supposed to go from 142 to 268, right? But for some reason I have to actually shift the first two data points, the first 2 time steps. I can either delete the first 2 time steps or just move those first 2 time steps to the end of the file, right? And then reduce this number by 2, and then reduce this number by 2, right? So these 2 numbers are basically just the index inside of this time series where it's non-zero, right? So it's a windowed thing, right? So everything is windowed, so it has a finite duration on the time series. The non-zero part of the signal actually starts from 140 now after this kind of modification, and then the ending time is 266 now instead of 268. So these 3 lines are actually metadata. That's not the actual time series, right? So this line is for recording how many WPKs I have, how many columns, columns I have in this particular file. So I've got just 1 column, and then the second number is time steps, the number of time steps, 471, the number of time samples. So that's everything that's needed in order to actually do the kernel calculation. So in order to run the kernel code, I have another. So basically, it's running this particular parallel binary. So this binary can run in sequential mode or in parallel mode. It doesn't really matter if you have more processes, then you can just run it in a parallel mode, and the number of processes doesn't have to be exactly the same as the number of processes used in the simulation. But for now, for this particular example, I was using exactly the same number of processes. So 10 nodes, 16 tasks per node, 160 processes. But it doesn't have to be. It doesn't have to be. It can be smaller than the number of processes used for uh, doing the wave progression simulations. And then the command line inputs, command line arguments. That's the inv.in file also used in the simulations, and then that's the directory for storing both the source wave fields, and the receiver wave fields, right? And then that's a list of all the WPKs or subprogram perturbation kernels, right? That's the three first input, and then the last input is argument is actually the directory in which I want to write out the kernel outputs. Right, so every process is going to write out its own output file, and then if the number of processes is smaller than the number of spatial partitions, then each of the process is going to write out more than one file, right? Each process is going to process more than one chunk, basically, spatial partition, right? So it's going to, but for now, because it's exactly the same as the number of partitions, so each of the processes is going to just write out the kernel file for one chunk. This is just a text file, so if I look at WPLX, that's the absolute path of that particular WPK. So now the kernel code is written in a way that's going to try to minimize redundant I/O, right? So it's important to actually cluster the the WPKs that's going to use the same source side wave fields together right next to each other, right? So if I have multiple WPKs that's going to use the same source, it's important to put those WPKs next to each other. Then the kernel code is going to try to avoid reading the same wave fields from the source fields repeatedly, right? And then if multiple WPKs are using the same receiver side Green's tensor, right, receiver side strand fields, then it's also important to put all those lines together, right? So and then the kernel code is going to try to actually avoid reading the same strand fields from the receiver side multiple times, right? That's pretty much the only thing that I have to sort of pay attention to, right? And then I can just submit this job, and then it's gonna do the calculation, and then create all those binary kernel files. Those kernel files are binary, so I cannot read them in the terminal. I have to sort of plot them using MATLAB. So for now, the kernel code has to be read and plotted using this particular script, read_ker. And then if I just execute it, it's gonna read the kernel, the binary kernel files one by one chunk at a time, and then assemble them together into like two different MATLAB arrays, and then this part of the cell is actually making a plot. The scaling isn't exactly correct yet. So the c-axis goes from like a -2 times 10 to the 5th power to a +2 times 10 to the 5th power. So that's one of the things that I have to figure out. But the thing is that it depends upon whether we're actually computing the kernels for the relative perturbation or absolute perturbation. So if it's computing the kernels for the absolute perturbation, that's in terms of the changes in the velocity. So it's got a unit of meter per second that's changes in the velocity, right? And then if I'm computing the kernels for the relative perturbation, that's not the changes in velocity, that's the relative changes in the velocity. So it's not the unit is not meter per second. It doesn't have a unit, right? So it's a change in the velocity divided by the reference velocity. So it's more like a percentage or sort of a fraction, right? If that's the case, the units for the kernels could be different, right? In this calculation, in the calculation that's done by Li Zhao, if I remember correctly, that's for absolute perturbation, I think. So the perturbation is supposed to be uh, the kernel is supposed to be relating changes in absolute velocity, that's meter per second, to changes in travel time, that's seconds, right? Um, did I? Did, but it doesn't have a color bar. So if you are computing the kernel for the with respect to the changes in absolute velocity, then the kernel's amplitude is supposed to be very small. It's like 10 to the minus 11, 10 to the minus 12, 12's power, that kind of thing. But if you are actually computing the kernels with respect to the relative velocity change, the fraction, so delta v over v, delta alpha over alpha, delta beta over beta, that kind of fraction change, then it's supposed to be bigger. It's supposed to be bigger, if my understanding is correctly. Maybe I said it wrong, but it's something that's kind of I have to pay attention to. I need to figure that out later on, but for now let's and then I can just run this particular script and then make those plots, right? So what's going to be the difference, right? I've got like multiple ones. This is the eighth, this is the fifth, this is the eighth, right? So if we compare it with Li Zhao's original paper, so I was plotting it in a way that's kind of can I rotate this view? I don't really know how to do that. So that's depth. That's depth. So free surface on my plot, it's on the right hand side. That's my free surface. I should have transposed the kernel matrix, right? That's free surface, and then that's depth. Again, this is depth, and then that's free surface, right? And then this is a plane that's perpendicular to the source receiver plane, and then this is actually looking at a plane that's kind of in the middle between the source and the receiver, right? How do I say? You can see some differences, right? But some of the things can be removed. So, for example, those whisks in Li Zhao's paper doesn't exist anymore, right? And then the sidebands, the sidebands depends upon the color scale that we are using, how much color, how saturated the color scale actually is. So the sidebands can appear in different ways, right? The strength of the sidebands can, but it depends upon two things. One is the filter that's used for computing the pre-filter that's used for computing the Green's functions, strand fields, Green's functions, and then also the whether we're actually making measurements on the velocity seismogram or displacement seismogram. It depends, right? Um, so here's a comparison. Here's a comparison. So this kernel is computed using a pre-filter for the Green's functions that's with a corner at 2 Hz and a order of 6. So it's a narrow band, right? The bandwidth is narrower. But this one is computed for using a Butterworth filter with a corner at 3.5 Hz and an order of 4. So this bandwidth is wider, and with a corner frequency that's also higher. Both of them are low-pass filters, right? Low-pass filters. So for bandwidth, if you have a narrow bandwidth, you're going to see more sidebands, and the sidebands are going to have a stronger strength. The intensity is going to be stronger. But the donut hole in the middle is like quite clear here. It's very clear. And then Um, and then depends upon display if you are using velocity or displacement. But my examples are just showing velocities, making measurements on the velocities. It's not using displacements. So if you are using displacement, I have a comparison that's in my book, but I didn't actually do that experiment here by using SW4. And then those kind of blue thing that's in the middle have disappeared, right? It doesn't have this kind of blue thing in the middle. This blue line thing doesn't have that. Right? So in my experiment, the source is here, right? And then receiver is here. That's the receiver, right? And then in this particular experiment, I think my I can't remember, but uh, I don't really know what Li Zhao used for as the source time function for computing the Green's functions. He was not using a filter, I think. He might be using the same Gaussian as the source time function for computing the RGT for the strand fields from the receiver, right? And if that's the case, uh, then his WPK, his Sudden perturbation kernel is supposed to be convolved with the his his, synthetic Sudden from the source side is supposed to have a Gaussian as the source time function in it, right? And then he needs to actually convolve that synthetic Sudden again with the same Gaussian if he was using the same Gaussian as the as a source time function for computing the Green's function for computing the Green's tensors. And then he was supposed to use that Sudden perturbation kernel when he compute the kernel, right? But maybe that's not exactly what he did. He was the effect of the Gaussian was pretty much just shifting the entire wave field by amount that's like b divided by 2, right? So it's like 0.325 seconds. That's a primary effect. It's just a delay. So if he doesn't want to convolve the Sudden perturbation kernel by the Green's function again, then he might just shift the RGTs forwards, shift the RGTs earlier to like 3.3 by like 0.325 seconds or something. That should also work, I think. Delay it or shift it. I can't. Delay it or advance it. Maybe I said it wrong, but the effect of the filter on the RGT is accounted for more accurately in those kernels. So there's no interference. There's almost no interference from other phases, right? You can see a cleaner kernel here, right? A lot cleaner. It's not symmetric. It's not symmetric because the source is explosive, but the Green's tensor is just a body force that goes to the x direction, right? So it's not symmetric. So this, if you see kernels on the computer using the adjoint method, you might see some kind of symmetric kernels, but it's not supposed to be symmetric. It's not supposed to be symmetric, right? Because the fields on both sides are different. This is an explosive source, but this is a body force with the x direction body force. So the strand fields on both on source side and receiver side are kind of different, right? Right. So you're not supposed to see a completely symmetric kernel, right? Because on the receiver side, the kernel is actually the source side wave field and the receiver side wave fields that's convolving in time at every grid point. On the receiver side, the receiver side going the RGT actually dominates. They have the biggest amplitudes, right? And the source fields the strand fields from the source side is a lot smaller than the strand fields from the receiver side. So what actually dominates is actually the strand fields from the receiver side, right? But on this point, on the source side, the strand fields from the source side actually dominates, right? And if the source side field source and if the source mechanism for the Green's tensor and the actual source are different, you are supposed to see differences in the kernels. So 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 that's one of the confusions people often have, right? And again, this kind of donut hole only exists if we are actually using broadband cross correlation travel time as our misfit measurements. If we change the misfit measurement type, for example, to an onset time, not exactly cross correlation travel time, I don't really know if this donut hole will still exist. Maybe they will disappear. Maybe they, I I have to do some experiments by myself to actually to to, to say for sure, right? Um, yeah, I think that's pretty much everything about the kernels. So this video is for kernel check, right? And it's actually the first kernel check. It's just a sanity check if the kernel is has the right shape or not. I haven't actually computed the kernels for the surface reflected and surface converted uh, waveforms yet, but I doubt if it's actually necessary. The next thing I want to do is to actually to see if I can get the kernels for onset time. Maybe that will be a failed experiment. I don't really know, but maybe I should give it a try, because lots of the misfit measurements are actually onset time. They are not really cross collision travel time, right? Um, and onset time, uh, for example, the first break is an example of an onset time. It's not really a cross correlation travel time. And another thing about the cross correlation travel time is that it actually depends upon the source mechanism, right? So if there's a big error in the source mechanism, or if we just don't have any kind of estimate about the source mechanism and we cannot actually compute the synthetic waveform accurately, then the cross correlation travel time could be affected by quite a big amount, right? Uh, so onset time, what's going to be the kernel for onset time? So um, maybe it's an experiment that's worthwhile.